Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you're interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is set queries. The problem appeared in November Cook Off and has a difficulty level of easy. The prerequisites for this problem are just observations. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the detailed solution approach step by step, followed by which we will be summarizing our solution approach and then implementing our code in C++. So before we begin with our problem statement explanation, note that this is an interactive problem. So let me just write down here that this is an interactive problem, meaning that there would be a grader and we are the user. So we will be making some queries to which the grader will respond, and based on that response we will be making our further queries and at the end would be completing the task given to us. So now that we know what an interactive problem is, let's begin with the problem statement. So the problem says that the grader has an hidden connected graph, triangle free graph with n vertices such that there are no self loops or parallel edges in the graph. So what do we mean by this? So the graph consists of n vertices, some nodes, right? And it is triangle free, meaning that no three nodes are connected in the following manner, such that they form a triangle. Also, there are no self loops like following, and also there are no multiple edges, like two nodes are connected by only a single edge but not a multiple edge. Okay, so there is a hidden graph with the grader, and to begin with the problem, the grader gives us some information to start with. That is, he tells us what is the total number of nodes, that is n. Then he tells us the degree of all these nodes, degree of all vertices, and additionally, we are also being given an integer k. Okay, so what is our task in this question? Our task is to divide the graph into two disjoint sets S and R. So let's say we have two sets over here, S and R. So we have to divide our given graph or the given vertices into these two disjoint sets. What are the conditions that we have to take care of? First is that each vertex must belong to exactly one of these sets. So if I number these vertices, let's say 1, 2, 3, 4 and 5, each one of them must go either in S or in R, exactly in one set. Okay, next, the size of the set S must be at least k. So the size of S should be greater than equal to k, pretty straightforward, right? But note that in constraints, it is also given one more condition, that the value of k is as follows. So this is given in the constraints below the question, but this is actually going to help us a lot in building the solution. So I'm writing it over here separately. Further, each two distinct vertices u and v belonging to S must have a distance between them greater than 1. So if there are, let's say, two vertices in S, say u and v in the set S, so distance u comma v must be greater than 1. Okay, this is another condition that we need to take care of. And further, for each vertex v belonging to R, so if there is a vertex v in the set R, then there must be a vertex u belonging to S such that the distance between them is 1. So for example, with this green color, if say there is a vertex in the set R, then for all vertices in set R, there must be at least like some vertex in S such that they are connected with a direct edge, meaning that d of u comma v will be equal to 1. So here it is given as shortest distance between u and v, but that is nothing but the distance between the vertices. So while taking care of all these conditions, we have to divide our set of vertices into two disjoint sets S and R. To do so, we can perform two types of queries. First is the query of type 1, that is 1 comma u. What this query does is it inserts the vertex u in the set S and returns us the list of all neighbors of u. So it will insert u in the set S and will return us a list of all its neighbors. The second type of query, that is query of type 2, 2 comma u, what it does not insert u in the set S, but it still returns us the list of neighbors. So these are the two types of queries with the help of which we have to perform the task given to us. So are there any other conditions as well? Yes, we are told that a same node cannot be inserted more than once in S, because we cannot insert the same node again and again in S, right? So that is one condition. And other is that the query of the type 2, please make a note of this, the query of the type 2 can be used at most once. It is given that it can be used at most once. So query of type 1 we can use as many times as we want, but query of type 2 has to be used at most once. So using these queries, we can request the grader to insert nodes in S and uh, divide the nodes, and at the end of our solution, whatever nodes we have inserted in S would be present in S and the other nodes would be considered in R. So we have to just make sure that all these conditions are followed, and we also follow the constraint on the type of queries asked. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. Now, to begin with the solution approach, let's start with some key observations. So observe that whenever we use the query of type 1, that is, let's say a query 1 comma u. So whenever we query 1 comma u, what the grader does is it inserts the node u into the set S. So let's call this node u, and what it does is it returns us a list of all the neighbors of this node u. So the node u is inserted in S and its list of neighbors is returned. So what I am saying is that ideally we should mark all these nodes using some boolean array or something. Like we should mark these nodes because these nodes should never be inserted in S. Why? Because it is given in the question that for all nodes u comma v belonging to S, distance of u comma v must be greater than 1. Meaning that if I have two nodes in S, the distance between them should be greater than 1. And if these nodes are the neighbors of u, it means that they are directly connected with the edge. So if this is u, then there are many neighbors of u, and this list is what the grader has returned us. So we mark these nodes so that we never insert them back in S. So where do we keep these nodes then? So all these nodes go in the R set. So let's say the nodes that were returned, we have put them in R. So if you are not inserting them in S, they are going in R. So they will go in R like this, and this supports one more point. That is, we now know that they are all the neighbors of U. So ideally they are connected with the edge with U. So the other property that was mentioned in the question was that for every node U belonging to R, there must exist a node in S such that distance between that node and U is exactly 1. That is, they are connected with a single edge. So this property is also supported here. So in this way, the key point to observe is that whenever we insert a node in S, whatever list it returns to us, we will mark those nodes so that they are never inserted into S again. So ideally they will go in the R set. So this is our observation. So now, based on the observations that we have made, consider the following process. So initially we create a Boolean array so that all nodes or vertices are initially unmarked. Okay, so all of them are unmarked initially. And now what does our process say? So pay attention. The process is as follows. First, we pick an unmarked node from the Boolean array. So randomly we pick an unmarked node. Then insert this node in the set S. So how do we insert a node in S? We have to use the query 1 comma the node, let's say u. So we insert this node in S and mark the node and all its neighbors. So this query would return us a list of neighbors. So we, whatever nodes are present in this list, we mark them as well. So let's say these 4 nodes were returned in the list, and this was, let's say, our initial node, say node u. So we mark all these nodes and continue with the process. That is, we keep on doing this process again and again until all nodes have been marked. So what is the process? We pick a node, unmarked node, insert it in S, say node U, then whatever list is returned, that list we mark it and keep it for R, and then continue the process. That is, pick again an unmarked node, we get the list, we keep the list for R, and we keep doing this process until all nodes have been marked. What this process does is it guarantees two things for us. One is that for all nodes present in S, all the pair of nodes present in S, the distance is always greater than 1. Why? Because the neighbors are always inserted in R. So no neighbor of node in S is present in S itself. So the distance between any two nodes is always greater than 1. And also, it also guarantees that whatever nodes are present in R, they have at least one node in S such that the distance between them is exactly 1 unit, because they are neighbor of some node, right? They are neighbor of some node which was inserted in S. That means that distance between V and that node, say U, is exactly equal to 1. So two things are guaranteed here. But the question mentioned one more constraint, that the size of this set S should be greater than or equal to K. So this process is not guaranteeing us this condition. Why? Let's take a counter example. So let's say we have a graph with us with 9 nodes and K is given as 2, and the graph looks something like a star topology. At center there is one node and there are 8 nodes surrounding it. So let's say at the beginning of our process, if we choose this central node to insert in S, what will happen is that this node would be inserted over here, say U, and all its neighbors would be marked and put in R. And this will end the process because now all nodes are marked, the central node as well as all the surrounding nodes. So the process stopped over here, but as we can see, K was given as 2 and we only have a single node in S. So there are fewer nodes in S than required. So it may happen that the condition of K is violated. So how to handle such cases? Let's see. So notice that the grader initially provides us with a lot of information, like the number of nodes n and the degree of each of these nodes, followed by an additional integer, that is k. So till now we haven't made any use of the information of these degrees of each node. So if we make use of these degrees of each node, we can classify our problem in two cases. There can be one case such that there exists a node in this degree array such that the degree is greater than equal to k for at least one node, or there can be a case such that for all nodes the degree is less than k. So we can divide the problem in two cases, and now we can separately discuss these two cases to reach the solution. So for case 1, if there exists a vertex with degree greater than or equal to k, there would be some nodes, let's say like these, some greater than equal to k count of nodes which are connected to a single node. Let's call this node as start. So there are edges like these going from start to these greater than equal to k number of nodes. So what we do is that we don't insert this start vertex in the set S. We don't do that. Rather, we use the query of the type 2, that is query 2 comma start, to get us the list of all these neighbors. So what is the size of this list? The size of this list is greater than or equal to k. Why? Because the degree of start is greater than or equal to k. We know that. So once we have this list, what we do is that one by one we insert all these nodes into S, these neighbor nodes into S, and the start node is kept for the set R. What this helps us with is that now the size of the set S is definitely greater than or equal to k, because all the neighbors of start were inserted in S and we know that the count of them is greater than or equal to k. So the size issue is now resolved, and we have also inserted the start node in the other set, that is set R. But now what to do for the remaining nodes? So we have taken care of this start node and all its neighbors, but what to do for the remaining nodes? So for the remaining nodes, just follow our old process, that is pick an unmarked node, insert it into S, and then whatever list is returned, mark those nodes as well, and continue doing these steps until and unless we have marked all nodes. So in this way, it is guaranteed that at the end of the process, the distance conditions are also taken care of, and also the set S contains greater than or equal to k nodes. For the other case where the degree of each node is less than k, if we pick up a random unmarked node and insert this node in S, so let's say I pick up a random node, unmarked node, and insert it in S, the list that would be returning would definitely be going in R. And the point to note is that the maximum size of this list can be k minus 1. It can be at most k minus 1 because the degree of each node is less than k. So in one iteration of my process, that is the process of picking an unmarked node, inserting it in S, and marking its neighbors and the node itself, in this one iteration, a total of 1 plus k minus 1 nodes were marked in total. This one node is the one which was inserted in S, and this k minus 1 are its neighbors. So in one iteration, a total of k nodes were marked. And as it is given in the constraints that k square lies in between 1 and n, we can guarantee that this iteration will happen at least k times, right? And in one iteration, one node was inserted in S. So what does this guarantee us? So in one iteration, if one node is inserted in S, in k iterations, at least k nodes will be inserted in S, and that is what we are aiming for. At the end of our process, there should be at least k nodes in S, and the other conditions of distance are already taken care of because the process is built in such a way that all the nodes in S are at least greater than one distance apart, and all the nodes in R have some node in S with which they are directly connected. So this process guarantees us both things. So to summarize our solution approach, initially we would be having a Boolean array where all the nodes are initially unmarked. Then first we will check if there exists a node with degree greater than or equal to k. If there exists such node, we would use the query of the type 2 and add all its neighbors to, to S and keep the node itself in R. Now, regardless of whether step 1 is performed or not, we would pick an unmarked node from our original Boolean array, insert it in S, and mark the node and all its neighbors, and continue this process until and unless all nodes are marked. So this summarizes our solution approach, and now let's see how to implement the code in C++. Also, did you know that CodeChef also conducts free live classes on Unacademy where we teach every possible topic on competitive programming? We have beginner level courses like Introduction to Programming in C++ or Java, basic data structures, recursion, as well as advanced courses like dynamic programming, graph theory, and segmentaries. These courses are conducted by top coding experts who have been ICPC World Finalists, IOI medalists, or have worked in top product companies like Facebook, Google, Amazon, LinkedIn. All you need to do is download the Unacademy app or register yourself at unacademy.com and select your goal as competitive programming. You can also take the paid plus subscription to get additional features and individual level support. In plus subscription, we have a large set of problems associated with each topic covered. Not only that, we also have 6-star and 7-star rated teaching assistants to clear all your doubts during and after the live sessions. Also, don't forget to use my referral code DarshanCool25 while subscribing to get an instant 10% discount. Now, to begin with our implementation, we start by taking the input for n and k, that is the number of nodes, and the additional integer provided by the grader. Now, once we have n and k, we have to create an array or a vector for storing the degrees of. So we create a vector of size n, and now we have to take the input for each of these degrees. So for int I is equals to 0, I less than n, I plus plus, we input degree of node I, and at the same time we maintain a variable start which denotes if there exists a node with degree greater than or equal to k. So if degree of I is greater than or equal to k, we update the value of start. And at the end of this process, we have with us whether there exists a node with degree greater than or equal to k and also the other information provided by the grader. So now, depending on the value of start, we divide our solution. So if start is not equals to -1, it means that we have found a node with degree greater than equal to k. Now it's time for us to start the actual query. So we create a boolean array named as mark of the size 10 to the power 5 plus some number so that we can store all the nodes in this boolean array, and initially they will be marked as false. And also we would be needing a function known as query which performs the query for us. So the function name is query and it should return a list. So we write vector int, and the function takes two parameters, that is the type of the query and the node we have to print. So we start with printing the type, then give a space and then print the node plus 1 because we are following 0 based indexing but the grader understands 1 based indexing. And finally we have to give endl so that the output is flushed. Once we print this query, we have to take the input for the size of the list that the grader is going to provide us. So we create a variable for that, int sg, and input the size, that is sg. Now we have to create a vector of the size, let's say sg, and take the input for the list that the grader is providing. So we can do that in the following manner. Note that the grader returns the nodes in 1 based indexing and we require 0 based. So after taking the input, make sure to write x minus minus. And that's it. After we have taken the input from the grader, we have to return this vector to our main function. Also, don't forget to mark the node as visited or marked once we have outputted it in the form of a query. So here we write mark node as true so that the node is marked true. Now coming back to the main function, if start is not equals to -1, it means that we have a node with degree greater than equal to k. So we start by using the query of the type 2. So the query would return a list. So we create a vector for that. Let's name it good, and we query with 2 comma start. So all the nodes that would be returned in the list are good because we have to insert them in S. So let's do that now. So for all the nodes in good, we have to insert them in S. So we have to use the query of the type 1. But again, that query would also return us a list. So for that, we would again create a vector with the name bad and use the query 1 comma node. Why bad? Because the nodes that would be returned are the neighbors of the nodes that we are inserting in S. So we have to mark them so that they are not again inserted in S. So we do that by writing for auto x bad, we have to mark x as true. So this ensures that the neighbors of start are actually inserted in S and their neighbors are marked true so that they are not again inserted in S. So once this process is done, now we have to take care of the other unmarked nodes. So we do that by writing a for loop. Now in this for loop, if the current node is marked, that is if mark of I, then it is of no use because it is already either inserted in S or we know that it has to go in R. So we continue. But for the unmarked node, what we do is that we have to insert that unmarked node in S. So again, it will return a list. So that list will be named as bad because the reason we know that the neighbors cannot be inserted in S. So we query 1 comma I, and for all the nodes present in bad, we mark them as true. And this process is done until all the nodes are marked because it goes from 0 to n, and if a node is unmarked, it marks it and also marks its neighbor. So this is our actual process that we discussed in the solution, and it will continue until all the nodes have been marked. And that's it. That completes our solution. The final thing remaining is that we have to output the number 3 so that the grader knows that we have completed with the task. Now, without wasting any time, let's submit this code on CodeChef ID and let's hope for a quick AC. Great, so our solution works.